Alright, welcome back, physics nerds. Now we're into the work, energy, and springs unit of this IA. And here are the following topics we're going to cover for this. It's quite a lot. This is a rather large unit, but it's not too bad, I say. And let's start with what work is. And it's not doing your homework. It's actually when you apply a force to an object that moves a certain distance. That's what we mean in the physics sense. Alright, and work is equal to the product of force and distance. W, big W, is equal to F times D, force times distance. And these two must be in the same direction. Horizontal force must move the object horizontally in order for work to be done. And this is measured in joules, therefore it's a type of energy. Okay. I also want to add a note here. If you ever encounter a graph of force times distance, for example, like this. Now, since work is the product of force and distance, you just got to multiply your force, your given force, and your distance. That's easy to say for this first part over here, because you have a constant force exerted over a distance. Now, what happens when we get to this bad boy over here, this triangle portion? Your force is not constant, so the work you exert is not quite the same as you would in the square portion of this. So that's why work on a graph equals area under the curve. So that means you gotta shade in the shape of the graph and figure out its area, and that gives you the work. Now let's get into power. Power is the time rate of work or energy. So this, our definition for power, is equal to work over time. And this is measured in watts. That's our unit for power. You can abbreviate watts with W. And if you look at this equation here, power is equal to work over time. Time is in the denominator. So that means if you have more time, you exert less power. If you think about it, energy per second, if you take more time to do the same amount of work, that means you have less power. Whereas if you do work in a short amount of time, then you have a lot of power. So more work also equates to more power. You could also expand this definition of power to equal force times distance over time, where you expanded the work portion of it into force times distance. You could also condense this into a shorter definition because of d over t. What is d over t the same as? Velocity. So here we have another definition of power, force times velocity. So if you exert force at a faster rate, then definitely there's more power. Now let's go into different types of energies, and we're going to start with kinetic energy, shown with this equation. KE is equal to 1/2 mv squared. Alright, work can be done to move an object and give it kinetic energy. So this kind of ties into our work energy theorem, where work is equal to the change in the object's kinetic energy. If it only gives it movement, then most likely it's just the change in the kinetic energy. And this is the energy of movement. That means we need velocity. If there's no velocity in this next bullet point, object at rest has no kinetic energy. Zero velocity, zero kinetic energy. An important note over here is the type of graph, the type of relationship between kinetic energy and velocity. If you notice in this equation right here, velocity is squared. That means it's an exponential or quadratic equation type of relationship. That means it's not just going to go up, it's going to go up a lot, like this. That's our graph between kinetic energy and velocity. This shows exponential or quadratic relationship. It's direct but not linear. It's exponential. Let me rewrite this. Next, we're going to get into gravitational potential energy, and this is depicted by this equation right here. PE stands for potential energy, is equal to mass times g, which is 9.81, times height, h. Unless you're on a different planet, then that g value will be different. But most of our problems we'll deal with on Earth, so g is still 9.81. Alright, so you can do work to lift an object. For example, me lifting a box, I'm doing work against gravity. So that gives the object potential energy. Because this is a stored energy due to position in gravitational field, this is also known as height. So the only way you can change your position in gravitational field is to go up or down vertically in height. So objects with zero height have no gravitational potential energy. So 0 for h equates to 0 potential energy PE. So because gravitational potential energy is dependent on height, it's often a type of question here when we're exploring the relationship between potential energy and height. Now looking at our equation right here, we're focusing on height. Because there's no exponent here, this is a linear relationship. So what would a linear graph look like? It would just look like this. That means if linear as opposed to exponential, they go up at the same rate and down as well at the same rate. So if height goes up by a factor of 2, so will the potential energy. As opposed to kinetic energy, if you notice, because velocity is squared, the effect is exponential. Alright, now we get into this idea of conservation of energy. Like in the previous unit about momentum, where momentum is conserved, here we also look at energy being conserved as well. So energy is neither created nor destroyed. But how do we kind of lose energy or gain energy? Well, that's because energy can transform from one form to another in order to conserve the total energy. You may end up losing kinetic energy. How? It turned into another form of energy elsewhere in the system. So a lot of the scenarios you'll see probably deal with free-falling objects, pendulums, roller coasters, or slides. And so the way we kind of depict this is where the total energy, and we typically break it down into kinetic and potential energy of an object. Initial is equal to final. So in the example of a falling ball, let's take that as our example. And it's held 2 meters high above the ground. So because of virtue of its height above the ground at 2 meters, and the fact that you're just holding it, it's at rest. Here at the top, you're always going to have maximum potential energy. Now, when it reaches the ground over here, because it's on the ground, there's no potential energy. But because it accelerated due to gravity, it turned all of that potential energy into kinetic energy. So that's why we have maximum kinetic energy at the bottom point. So let me just add some point here. Max potential energy, no KE. Over here, max kinetic energy, no PE. So it's a complete conversion from one form to the other. If you end up somewhere in the middle over in this free fall, then there's a mix of both potential and kinetic energy. You can still have a mix of both, but always at the top you're going to have max potential energy, and at the bottom you're going to have max kinetic energy. These are safe assumptions you can make at this level of physics. If you're going to go into higher levels, then you can't exactly make that safe assumption. This is the same for pendulums and roller coasters. Max potential energy at the top, max kinetic energy at the bottom. You can always equal one to the other. Alright, now let's go into internal energy. So before we've talked about kinetic and potential energy, and the sum of those two together is what we call the total mechanical energy. And this is typically what we use for conservation of energy problems. However, you're probably going to see real-life scenarios in which it's not conserved. The total mechanical energy doesn't add up on both sides to be equal. That's because we have this thing called internal energy, and this follows more real-life examples. For example, a bouncing ball. Because in real life, we often hear sound, and there's also friction. When those two are involved, then that's when we have internal energy. That sort of accounts for the discrepancies in total mechanical energies from before and after. This is where the lost energy goes. And let's take a look at our bouncing ball example. So let's say at 2 meters high, you have a ball. You bounce it, hits the floor, bounces back up, but not quite at the same height as before. Why is that? When you bounce a ball, you probably hear a sound. And there's also air resistance involved. That's internal energy. So because of this loss of mechanical energy, it probably transformed into internal energy. And at the same time, because of that, we still managed to conserve total energy. And so we could write this as E total is equal to KE plus PE plus Q. So if your total energy, kinetic and potential energy, doesn't add up to what we expect as our total energy, then there's likely that missing piece is internal energy. That's when friction and sound are involved. Now let's start talking about springs, and we're going to start with Hooke's law. And this is exemplified by the statement, which we could sort of write out as an equation, where the force applied to a spring is directly proportional to the compression or extension of a spring. Fs, force in a spring, is equal to K times X. K is our spring constant. It's characteristic of different springs, how stiff or how loose a spring is, whether or not you need more force or less force to stretch it or compress it 1 meter. And X stands for compression or extension. Now let's say you have a force hanging vertically, and there's a weight attached to it. This over here, this weight, the force is equal to its weight. You could have the same sort of scenario happening if you have the spring attached to the ground and you have the weight attached on top of it to push it downward. So once again, the force is the same as the weight of the object applied to the spring. Okay. Now what's important here is the relationship between force and the compression or extension. So if you see this type of a graph, force times distance or force times x, force and x, see this type of a graph. The slope of this line is equivalent to the spring constant K. So the steeper the slope, the stiffer the spring, the higher the spring constant, whereas a gradual slope stands for looser springs, smaller K constants. Okay, and it's a linear relationship. That means they go up at the same rate. Alright, now this leads us into our final concept of the video, the spring potential energy. So this we represent as PE S, subscript S, standing for spring. So this is different from PE equals mgh. This is PES, which is equal to 1/2 kx squared. So k is still there, our spring constant, but this time we have a 1/2, and that x is squared this time. And this is our stored energy in a spring. So when you compress or extend the spring, there's energy being built up inside the spring, and once you release it, something happens. And so you can also apply the conservation of energy law to springs. For example, let's say you have a spring here attached to a cart. Okay. So after you release the spring, the cart is going to shoot out. So in this scenario, energy in spring becomes movement for the car. So here we see a transformation of spring potential energy into the car's kinetic energy. So whatever amount of potential energy you have in that spring, you can easily equate it to the kinetic energy of the car because it's a complete transformation of one form into the other. All right. And also, last thing about relationships between variables here. potential energy in the spring, and the extension or compression of the spring, X. Looking back at our equation here, since we're focusing on X, notice here the exponent. What kind of graph does that make? It's an exponential graph, like that. It's a quadratic exponential relationship. And that's it for this video. We pretty much covered some of the gist of these topics. A lot of this IA is going to be calculation based, which you could just rely on the reference table for the equations, but always be sure, do not get tripped up on the wording. Other than that, good luck guys.